start the morning after the conference dinner, but we have to start with Swiss precision. It's a pleasure to introduce the plenary speaker, Manfred Sigrist, and the title is
Thank you very much. So I would like to thank the organizers to invite me here to this very nice place and to this very interdisciplinary conference. Of course, it's my most favorite slot to have the first talk after a conference dinner. Then you can really see who is keen to hear what you are talking. So, I will talk today about true and nearly multi-component superconductors, and I think during the talk it should become clear what I mean when I say true and what I mean when I say nearly. This encompasses a lot of work done over the last 10 or so years, and so I have a lot of collaborators. I will not go through all the list, but you may recognize many of the names. And so let me start slowly, just introducing the concept of unconventional superconductivity. So the Cooper pairing symmetry is an important concept here, and so you are all familiar with what we call conventional superconductors. The Cooper pairs form in the lowest angular momentum channel with a spin singlet spin configuration to keep the Pauli principle. And so this is usually called S-wave pairing. This has a unique single component order parameter. If we go unconventional, this means we have higher angular momenta. So we often call this P or D-wave pairing, just referring to angular momentum, even if angular momentum is not a good concept. And in this case, when we have even L, we have spin singlet. If we have odd L, we have spin triplet pairing. And here, of course, we have the possibility to go to degenerate order parameters, and so we have naturally multi-component order parameters. The choice of the stable phase, of course, depends on many different aspects. The pairing mechanism, condensation energies play a role. Spin orbit coupling can play a role if we have, for example, not singlet singlet spin configuration. So examples of degenerate order parameters or multi-component order parameters can be found, of course, in helium-3. We have heard about this during the conference, and also an early example where it was clear that there is more than one order parameter component is, for example, toriated uranium 13, where we have various different superconducting phases. You can only think about this when you have more than one order parameter component. So let me quickly go into helium-3. Helium-3 has two phases when we do not apply magnetic field. We can represent the pair wave function in a 2x2 matrix with the different spin configurations. This is the normal state symmetry, full rotation, speed rotation, time reversal, and U1 gauge symmetry. We know that helium-3 has an order parameter in the L=1, S=1 channel. This gives 9 complex order parameter components. And so with the condensation energy, with the pairing mechanism, we can get two different phases. At ambient pressure, we have the B phase, the Ballin-Berghammer phase. It's this phase here. It's unique. It has intrinsic spin orbit coupling. If you look here at the symmetry, this one is running out of battery. Let me try with this. This means we have a dynamical type of spin orbit coupling, so this has a full gap. And as I said, it's unique. On the other hand, the A phase is stabilized by spin fluctuation mechanisms, and so here we have a lower symmetry where we have a funny type of chirality symmetry here where angular momentum and the gauge phase are coupled. This is the so-called chiral phase, and it breaks time reversal symmetry. Oops. Now, in this talk, I will touch two materials. I look at strontium rusinate, which is an example of a chiral P-wave phase. At least that's what I believe. There is a certain controversy on that. I will not touch the controversy, but I would like to promote the multi-component aspect of this material. And so don't pin me down on the controversial experiments. Just leave them on the side. And the other one is a heavy fermion material, which is a non-centrosymmetric material where we have mixed parity pairing. And so I will show you here we have something which is a nearly multi-component order, which has a nearly multi-component order parameter. So let me start with the strontium rusinate. Strontium rusinate is has a layered perovskite structures. The important thing are the ruthenium oxide layers. So this structure is very similar to the cuprates. You can see the Fermi surfaces here by Behaas van Alphen and Andy Mackenzie's group. We have 3 Fermi surfaces. They are from the 3 D2G ruthenium orbitals. It's really very two-dimensional. These are basically cylindrical Fermi surfaces. Also in the transport, you can see that we have a very high ratio among C-axis and AB plane connectivity. Both directions are showing T-square behavior at low temperature, so it's a good metal when it becomes superconducting at 1.5 Kelvin. And so it was early on realized that this superconductivity is very fragile, so a little bit of disorder will kill superconductivity. So here you plot it against the residual resistivity. Here you plot with iridium or titanium, and so the resistivity goes down. It follows very nicely the expected Abrikosov-Korkov fit, and so in that sense this is textbook-like. So you need a very long mean-free path to get this thing superconducting because the coherence length here is of the order of 700 angstroms. Now, the idea came up looking at this material that this could be an analog of helium-3, and so helium-3 I just showed you before the 2 phases, B and A phase. Now I represent them for convenience by the D vector. I hope most of you are familiar with that, so I can represent the 2x2 matrix in terms of a vector. And so the B phase looks like this, the A phase looks like this. And so if I now look what phases are possible, if I have, instead of full rotation symmetry, just the tetranal symmetry, I have also strong spin-orbit coupling, means that the spin and the orbital part transform together. And since it's highly two-dimensional, I assume that I have only in-plane pairing, so I have no KC component. Then I get all these phases here as possible phases. I have 4 one-dimensional ones and 1 two-dimensional one. The one-dimensional ones are B phase-like. The two-dimensional one is like the A phase. That's more obvious than this here. Now, looking at the experiments, now I really cite only those which are favorable to my case. Don't put me down on that. I don't want to go into the controversy of nature or of the order parameter in these materials. I want to show you multi-component aspects. So here is the spin polarizability by night shift, measured by night shift. With the in-plane field, the susceptibility doesn't go down. So this means we have equal spin in-plane, equal spin pairing. This means the D vector is pointing along the C-axis. At the superconducting transition, we find internal magnetism by USR experiments. And this points towards time reversal symmetry breaking. So, and this comes really only at the superconducting transition. Then, looking at the field distribution, if you apply a field along the C-axis and look at the mixed phase, you see saddle points, which you can only explain if you have a 2-component order parameter. And then we have in ultrasound, we have a sound velocity realization for transverse modes. This is not possible for a single component order parameter. You need at least a 2-component order parameter. I will dwell on this a little bit more later. And so the one state which fits well with this is the A phase-like state here. And so just to characterize this, so the D vector looks like this in the 2x2 matrix pair wave function. So we have these off-diagonal matrix elements which have this chiral type of configuration. This is a spherical harmonic basically, and under time reversal, of course, we get the state from the plus to the minus state. So this is indicating that we have broken time reversal symmetry. We have degeneracy 2 here. This just tells us we have a 2-component order parameter. This is also a topological phase, and so the analog of the helium-3 A phase with this symmetry here. So we have the angular momentum along the z-axis, and we coupled with the gauge transformation. So rotation around the z-axis is equivalent to a gauge transformation, and also the sz component is conserved. And if I now look at what I have here, the spin rotation means I have equal spin in-plane pairing in terms of triplet pairing. This is this sz equals 0 state. And I have the angular momentum pointing along the z-axis, and so since they are charged particles, this would also produce magnetism, the one which we saw in the MultiSuper. Now, this is intrinsically two-component order parameter. I said before, we have degeneracy 2. I can represent an order parameter by x and y component. I have a kx and a ky component, so if I represent a d vector by these two complex order parameters, then the stable chiral p-wave phase is given in this way. I can write down the Ginzburg-Landau free energy, which is a little bit more complicated than the standard single component Ginzburg-Landau free energy. You just write down what is allowed by symmetry. The free energy has just to be a scalar. So then it becomes a little bit more complicated. You get a very interesting phenomenology. Now, just based on that, I would like to show you that now, for example, coupling to strain or ultrasound is very interesting in such a situation, because if I look at the strain here, that's just this derivative of the displacement field, then I can also again create scalar terms in the free energy, coupling to the order parameter to the strain, and so the order parameter has always to be quadratic in order to be gauge invariant, time-reversal invariant. And so looking at this here, this is strain corresponding to a uniform pressure or longitudinal sound modes. And this couples to the modulus. And so this term we would also have here a single component order parameter. However, what is unconventional here is the coupling with shear modes or shear strains. They are only possible when I have more than one order parameter component. And so uniaxial stress couples to this, but also transverse sound modes. And so now I have, for example, applying uniaxial stress lowers the symmetry. X and Y, for example, are not the same anymore. So I can induce double transitions, for example. And if I see a double transition under such a situation, I would have a good proof for a multi-component order parameter. People have tried that. So far, this was not successful. You can shift by uniaxial stress. You can shift the transition temperature. You can lift it by applying uniaxial stress. There's usually the transition temperature goes up if it's in plane. And so this is already a hint that you have a two-component order parameter, but you don't see the splitting. So this is a multi-component feature. And the other thing is that these shear strains here are connected with transverse sound modes. And so you can change, for example, the sound velocity in the superconducting phase through this coupling, and so that's here. Lupien and Dreifer here have seen, for example, in the transverse 1-0-0 mode, you see a clear step in the sound velocity. So, and this we would not see when you have a single component order parameter. Now, I would like to show you a feature where where I believe that the multi-component aspect comes out neatly, and that is seen in the filamentary 3 Kelvin phase. And so the 3 Kelvin phase, actually, that's something showing up in eutectic materials where strontium leucine is penetrated by ruthenium inclusions, micrometer-sized inclusions. So this is something Meiner and this group found in 1997. And so here you can see a picture. So that's this bright stuff is the ruthenium inclusions. Here it looks rather regular because that's the plane here of crystal growth, but if you cut transverse, then you see it's a little bit of a mess. But so these are micrometer size inclusions. So if you have a pure material, you have a sharp transition roughly around 1.5 Kelvin. Here a little bit lower. The sample is not that pure, but it has no ruthenium inclusions. If you have ruthenium inclusions, then you have a broad transition. The superconductivity has an onset into inhomogeneous superconductivity already at roughly the double transition of the bulk transition. And so since Tc in the pure sample is roughly 1.5 Kelvin, this would be roughly at 3 Kelvin, not in this sample though, but so this gave the name 3 Kelvin phase to this inhomogeneous phase. Now, the question is where it's coming from. It's not the superconductivity of ruthenium. Ruthenium is superconducting at 0.5 Kelvin, and we know nowadays that it goes at this temperature superconducting in these inclusions. And so we had the idea that then it must be possibly an effect of the interface, that at the interface, for some reason, Tc is enhanced. This is maybe a strain effect, and so an enhancement of density of states. We don't know really. However, we just assume that this is the case, and then you can ask yourself what state would be nucleating in a strontium rusinate side. We have two possibilities, and what you see is that the one with the p lobes parallel to the interface is favorable. The thing is, of course, you have we have Cooper pairs which stay in the good region. If you have perpendicular, they move out. So you would like to keep them here. And so now, this is a filamentary phase, and so we can see in experiments actually that this is filamentary. If you look at HC2, when you apply a magnetic field, then you get sublinear temperature dependence of the upper critical field. That is a sign of filamentary behavior. Even you can see, if you look at the field along the z-axis, you have here this upturn. And this upturn is actually quite good sign for inhomogeneous superconductivity, and from the place where the upturn appears, you can estimate what is the size of the good region. That's 200 nanometers. That's a good, reasonable number, so we are not having some very strange conflicting input here.
Sorry, but here AC2 goes to 0 at the T star, let's say, not the TC.
Yeah. This is the onset of the downturn of the resistivity. So it's the onset of the 3 Kelvin. Of course, the real HC2 is here, starts here, roughly. Now, the question is, if I start with this here, of course, this is not the chiral P wave phase. The question is, how do I get eventually to the chiral P wave phase? This here, if I now look at the situation where I have a closed interface, so an inclusion surrounded by strontium rusinate, then this P wave state would nucleate in such a way. It looks like ants walking around all the same direction. So we have, in that sense, the same phase if you walk around, but if you look here at transverse, there is a pi phase shift. This ant moves in that direction, the other direction. Now, this is not the chiral P wave phase. Now, what could happen is that we do a second order phase transition to break time reversal symmetry by adding the perpendicular component. And so then we would have added in a complex way, so that we have here locally chiral state. But this has, from topology, still not the behavior of the chiral P wave state. The chiral P wave state is something like that. Here we have pi when we transverse. Here we would not have pi. Here we have 0, but we have an overall phase finding if we look just at the parallel phase. So we have here a different topology than we have here. And so from here or from here, we would have a first order phase transition into this state. And so the question is now, what does the sample do if we go down in temperature? And so we did an analysis of Ginzburg lambda of free energy. And what we found is you go first into the A phase, and then you jump into the B phase. This is a change of topology here. This is a first order phase transition. Weakly first order though. And then the B phase has the right topology for the bulk state. This is a chiral state. And so we have here then only percolation to the bulk phase. Now the question is, do we see something like that? So this is now a real sign of multi-component superconductivity. And actually there are two experiments which fit into this feature. And that one is looking at the critical current in the 3 Kelvin phase. This critical current is just where do you see an anomaly in the IV characteristic if you do run a current. And the other one is tunneling. And so let me just quickly show you what I mean by the critical current case. So you run current in blue or the reverse red direction. And so below a certain temperature, 2.3 Kelvin, this does not give the same critical current anymore. Above, it gives. Now, we can understand this through a network behavior. The system behaves like a complex Joseph network, but once it breaks time reversal symmetry, then you can show already in a very simple Swift type of model that you would have different critical current if you run the current in this and the other direction. Now, let me look at the tunneling. In tunneling, already in 2000, Ying Liu, Mao, and co-workers found in break junctions that actually you see, within the free Kelvin phase, you see zero biasymmetries showing up. And so, a little bit later, people succeeded to make contacts to single ruthenium inclusions just from the top. You contact them, and then you make tunneling through this, and so here you see also zero bias anomalies. Here now as a function of temperature at low, as a function of field at low temperatures, but you see here clearly these zero bias anomalies showing up. And so the question is how this does fit into the picture, and so where do these zero bias anomalies show up? So first of all, if I have the A phase, I have my loop parallel, then this will not give rise to zero bias anomalies. It will rather, the characteristic of tunneling will look somehow qualitatively like this. We have here a V-shaped type of behavior which corresponds to the nodes which we have here in the gap. Now, if I have a perpendicular component, this perpendicular component means I change sign under reversal on a plane here. In addition, I have the phase, so I get something which is a chiral edge state. So here it's just schematic, so this would not necessarily look in this situation like that, but so from topological point of view, we have such a state. And so this here gives rise to zero bias anomalies. This would look roughly something like that, also again qualitatively. And so when you have the second component, you would expect a zero bias anomaly, not when you have the first component. So this here is mimicking roughly this. So here I have now data in a magnetic field. So we have the red and the blue points. They correspond to fields in the plane, in the basal plane of the material here along the z-axis. And you see both merge here to 2.3 Kelvin, like where we have the anomaly showing up in the critical current. So from when you come here, from here on, you see zero bias anomaly, zero field. Now, that are the critical fields which I have seen before. These are the onset of the 3 Kelvin phase, and here the red points are the onset for parallel fields, and so this is slightly lower, always slightly lower. And then we have the field along the z-axis, which here merges with the onset field. And so we believe that this very much fits into the picture. First of all, that we have here an onset at lower temperature means that the perpendicular component has to show up to see the zero bias anomaly in agreement with what one would expect. And secondly, that this merges with the onset of superconductivity, or of the 3 Kelvin phase, when we have the field along the z-axis, has to do actually with the fact that if I have the perpendicular component in addition to the parallel component at the interface, I produce a Cooper pair with angular momentum. So I can have the same uncoupling to an order parameter like that. So this is the, in terms of these two components, I have the angular momentum like this. And so then I can introduce in the free energy a same uncoupling term to this angular momentum. And so once I have one component, say the X component here, and I have a magnetic field, then this is a source term for the perpendicular component. And so immediately when I turn on the field, this starts to come up. And so when I have high enough fields, then always with this component has to show up. So they come together. So this is we consider as a kind of proof or indication that the chiral P-wave concept is not so bad. So that's now all I would tell about Johnson resonate, and as I said, I will not touch the controversy. So there are controversial experiments for the chiral P-wave states, for example, missing, so the negative result of trying to find edge currents in this material, although we can see the zero bisimilarly being in agreement with chiral edge states, we cannot see the currents or the fields produced by the currents. But we can see the fields by muons in the sample. So we don't really know at the moment how to deal with that, but time will probably solve the problem. So let me come now to the other part. So here now, so far I've told you something about the true multi-component order parameter. Now let me come to another subject which I introduced via this material, cerium platinum 3 silicon, which is a non-centrosymmetric material. This is a heavy fermion material found in 2004 by Ernst Bauer. Has a rather low TC of 0.5 Kelvin. This is the crystal structure. And if you look at this crystal structure, then you immediately realize this is a non-centrosymmetric material. If you apply inversion, then you turn this on the head, and this is not the same crystal structure. So the pyramids, which are illuminated upwards, are now here downwards. And so this is not the same crystal structure. And so the question is, what implication does this have? And the implication is basically that we have, in this material, in addition to ordinary spin-orbit coupling, we have Rashba type of spin-orbit coupling. This structure here is somehow mimicked like a metallic thin film with a transverse electric field. And so we have this Rashba type of spin-orbit coupling, which leads then to a spin splitting of the electronic state. So we have this funny winding here of the spin polarization axis around. I will show you afterwards, just in the, or here, yeah, you can see when I project it on the basal plane in K-space, you have this funny winding of the polarization axis. And so Carlos Sadamelo had also shown this in his talk, and so here we completely are parallel. If I have this, of course, I change, so if I turn on this spin-orbit coupling, I change the structure of the electrons at the Fermi energy. And that's where we form Cooper pairs. And so this means then the spin structure which I introduce here by spin-orbit coupling, of course, determines Cooper pairing symmetry. And what we have is mixed parity. So writing down the pair wave function here now with the Pauli matrices, I have an even parity part, and I have an odd parity part. The even parity part I always represent here by an amplitude psi e, which is a complex, and psi O is for the odd parity part. And the odd parity part carries the spin structure, or the vector structure, or spin structure of the Rashba spin-orbit coupling. So whatever you have here, you can plug it in here, and you get the right pairing structure. So here, of course, I don't know what is this dominant, is this dominant? If this is dominant, then this will be just by spin-orbit coupling introduced. If this is dominant, it's the opposite way. So they are just coupled. So this is a mixed parity pairing because we don't have parity anymore as a symmetry. So this is in principle nothing spectacular. It's just reduced symmetry, and you do you change, you twist a little bit your order parameter. If I write it out in terms of the 2x2 matrix pair wave function, then I see that I have this structure. So the even parity part here is off diagonal, up, down, minus down, up. This is singlet. And then I have here up, up, and down, down with opposite chirality. Opposite chirality. So here the spin up, up goes with down angular momentum, and the down, down spin goes with up angular momentum. This is helical. This is a helical state. So if I look at the symmetry of this state, I keep time reversal symmetry, unlike for the phase which we had before. And I have for the U1, I keep U1 symmetry where LZ and SZ are coupled here. So this is very analog to what I find in the B phase of helium-3, And so we have some of the aspects of helium-3, but not all, because helium-3, of course, doesn't have this even particle part. And so now, this is under some conditions, if the odd parity part is dominant, this is actually a topological superconductor. It has helical edge states, so with spin currents and so on. I will possibly touch on this when the time, if I have sufficient time. But so now I would like to look at how I can generate here a multi-component order parameter. So I look at the twin boundaries now, where I can twist the order parameter. So now if I look at this state here, this is not, of course I write it here as if it were a two-component order parameter. I have an even and an odd parity part, but this is just a pure convenience to write it like that. I could write it in any way. This is one single order parameter frozen by the spin-orbit coupling, and so this is not a two-component order parameter. However, now if I look at this here, at this crystal, and I would write the wave function down like this with a plus sign, as I have it here, and I apply inversion operation, then I get a minus sign here, because this part here changes sign under inversion operation. Not the even parity part, but the odd parity part. And so now, let us look at the crystal where both types of crystal structures appear. And so, of course, if you grow a crystal, you can, it actually happens quite frequently that you have twinning of the crystal structure and then twin boundaries between such regions here. And so you have to ask what the superconducting order parameter does if it comes to such a situation where the two order parameters on the two sides are different and you have to match them in some way. And so let us look at this situation. So I have even odd parity part here. I have a domain with plus, and I have a domain with the minus sign, the relative minus sign. I write down now my order parameter in a way that I have psi e plus psi o and a phase, which I call phi plus. And here I have just with the relative minus sign a phase phi minus. And so now, looking at the example that the even parity part is dominant, then I would like to keep the phase of the even parity part constant and let the odd parity part switch sign, and so the matching would look somehow like this. If I go through the twin boundary, I have a kink in the odd parity part, not in the even parity part. So now I can, of course, start to shift weight. I can increase the relative magnitude of the odd parity part and look what I would expect. If the even parity part is by far bigger than the odd parity part, then the relative phase, or the phase difference between the two sides, which I call now phi, is just 0. I would just get this situation. Psi e is constant, and psi o would change sign. If I go the opposite limit, then of course I would have to turn around this picture, and the odd parity part would be constant, and the even parity part would have to change sign. So the relative phase, the phase between the two sides would have a pi. These are unique states, 0, and here plus or minus pi over 2 is just the difference of 2 pi, so these states are the same. And so I make here now a graph as a function of changing the relative magnitude of even and odd parity part. Now, there is a region in between where the two are comparable, and so what you find is actually that here the phase changes continuously if you go low enough in temperature. There is a window here, and this window, if you go to the look at the phase diagram Tc versus this R, which describes the relative magnitude, this window grows. So this is just a schematic structure. So we cut through here, and then we see that we have here two intermediate phases. Now, this phase and this phase are not the same. They are not different by 2 pi. When I apply time reversal operation, I go from here to here. So I have a twofold degenerate state which breaks time reversal symmetry. And so now I have twofold degeneracy. immediately I have a two-component order parameter. I've released it by twisting the order parameters. And so now you can also look at it from a slightly different point of view, which will be convenient to look at phenomenology here. I have the two components here. I leave away the overall phase, but I take in here the relative phase. And the relative phase, when I'm in here, is going either from 0 to plus pi or to minus pi. I have two types of, so these two types of twin boundary states. And that's now, also here you can see this, is, you can see that when you go through here, you have here gamma. It's sharp if you are outside here, it's just a sharp step, and so here it's smooth in the middle for the relative phase. Now, if you have such a twin boundary, you may of course have on the same twin boundary both the A and the B type of states. Here for the B you go with gamma in the center through minus pi over 2. In the A state you go through plus pi over 2. And so here you have gamma pi and here you have gamma 0. And so what you have here is a line defect, and if you go around here, you have a phase winding of the relative phase. This is a vortex. You have a flux associated with that, but what you see is this is not a flux with of the overall phase, but it's a flux of the relative phase, and this gives you generally a flux line which has a fractional flux only. And the fraction is not half, it's just anything, so it changes also with temperature. But what you can say is, if you have two neighboring flux lines, so you go from B to A to B, then around here you would have standard flux quantization. So they should add up to an integer flux quantum. And so we actually got to this discussion here through some experiments done by Celia Motta and co-workers. And so what they saw is in this material they have they see a very low flux creep rate. And so the idea was basically if you have twin boundaries and vortices get on the twin boundaries and we have the possibility to split the flux, then it will do it because it can lower the field energy. It's always better to have smaller flux. So they will do that. And once they are split, they are fixed on the twin boundary. In order to get them off the twin boundary, you have to recombine them. So the idea was when you put flux in, then some of the standard, so if you put a lot of vortices in the material, when you do a flux creep experiment, some of the vortices will go on the twin boundary, split up, and they will make a fence, an impediment for the flux flow. That we believe gives rise to this very low flux creep rate compared to other materials like the superrhodite or the uranium-barium-13, which are quite comparable superconductors. But this would not be the whole story. Of course, you could say, okay, so you have very strong flux spinning here. But this is not the case. Individual flux spinning is rather weak here because the critical currents are extremely small in this material. So you need a mechanism to an impediment of flux flow which has not to do with the individual flux pinning, which limits the critical current. So we thought this may be now one possible explanation that we have, that twin boundaries would act as fences once we have flux in. But so just to show that here we can have interesting multi-component order parameter showing up. It's not a true multi-component order parameter, it's a nearly multi-component order parameter which you can release with twisting. Now, before closing, let me just quickly show how the story goes on. If we have time erosion symmetry breaking in a superconductor, usually we have spontaneous currents, we have magnetism. You can show that this is not the case here. And so the reason for this is that this order parameter combination cannot couple in lowest order to a magnetic field, or that's sort of the symmetry reason for that. What you have when you come into this phase is that you have, before you come into this phase, you have U1 gauge symmetry, time reversal, you have a mirror symmetry, a mirror plane just being perpendicular here to the twin boundary. Now, on this twin boundary, you have spin currents running. This is an aspect of Rashba spin-orbit coupling combined with superconductivity. And so you have a phase diagram now like this. Out here, U1, so everywhere below TC, U1 gauge symmetry has gone, but we have here time reversal times P2. Here time reversal times P2. Here we break time reversal symmetry, but this is not a magnetic phase. And what we find when we go on is that we actually get magnetism at the lower transition temperature. And this then is combined with spontaneous supercurrent. So here we have spin current, we have a spontaneous supercurrent. And the superposition of supercurrent and spin current gives us a spin polarization here in addition to the magnetic field, which you also drive here. So we have here even a further order parameter which can show up. And so I'm here at my conclusions. So first of all, I have shown you the time reversal symmetry breaking superconducting phase, which is genuinely multi-component. You cannot get time reversal symmetry breaking without being multi-component because you have a degeneracy which you built in. This degeneracy can give rise to all the funny phenomenology, like for example domain wall formation or domain formation, and so you have some topological defects with which you can play. Also for this in strontium-rusinate, there have been some experiments in Dale von Harlingen's group some years ago, which fit very well actually into the picture. Then coupling to symmetry breaking fields can give rise to many interesting features. I mentioned couple transition, unusual responses which we do not expect for a single component order. Under some conditions, a single component superconducting phase can be susceptible to local multi-component feature. When we twist the order parameter in some region, then the order parameter may escape into a larger phase space, and this would often give rise to time reversal symmetry breaking. So you can lower your energy by just not forcing an order parameter component to go through zero, for example. And so something which I didn't talk really about is that such local phases may have very interesting properties also when you apply certain fields, magnetic fields, for example. And so with that I'm done, and I thank you very much for your attention.
So, we have time for questions, please.
But is it possible to generate these fractional vortices even without external magnetic field?
Oh, they are not coming spontaneously. They cost energy.
Yeah. Because of the energy. So
yeah.
It's just when you put the magnetic field, you can generate it.
So a vortex comes in from outside. It goes to the twin boundary. It would anyway go to twin boundary because it's also an ordinary pinning center, but then it splits up. And then these vortices are just tied to the twin boundary.
How many of these you depends on the total?
On the total flux. Yeah, there's a flux pressure basically. There is a certain density when the vortices, of course, pinned vortices come too close to each other, then they are easily recombined, and so then the wall becomes transparent. So you can ramp up the field very high and you get the flux in, but when you afterwards want to get it out, you will have a beam profile within the sample. When here is the twin boundary, you have a beam profile, and so what you have here is just the critical density of vortices that you cannot depin the twin boundary vortices.
Question, I mean, in your description you have time reversal symmetry breaking.
Yeah.
And once in a while we also have parity breaking.
Yeah.
I mean, my understanding, correct me if I'm wrong, that in your original theory you have some kind of CPT invariance. I mean, the theory is invariant under P and T. So it means that if you have time reversal symmetry breaking, you must have some parity breaking also.
Yes, so if you have the chiral state, of course, if you take the parity operation, x goes into x and y goes into minus y, then that's basically doing the job. Yeah.
I think just on that point, I mean, CPT is not necessarily conserved in our progressive mapping system. So we can break CPT, we can have states that break CPT.
But with the theory of the world, that's not very clear.
Seems like a long discussion. There was a question in the back.
Yeah, in Sadimir's talk, he mentioned something like when you go from two phases with topological phases, what remains is a Majorana zero energy mode, right?
Mm-hmm.
And you show like some chiral edge state in the negative one. I mean, if it's also originally it's possible to find Majorana zero energy mode when you go from one topological, if there are two topological.
Yeah, so I mean, you find these zero energy modes in principle if it's really the chiral p-wave state, so which not everybody believes, but so then you would have the zero energy mode. Of course, it's in a continuum of states, so it's not a separate state, an isolated state. Some people say only if you isolate it, it's a real Majorana. But so in that sense, you have this zero energy state at the edge. Also at domain walls, you can have these kind of states when you go between two different, so up and down angular momentum states. Then you have two modes at the domain wall with a similar property. And for the non-centrosymmetric state, if the odd parity part is dominant, then for a certain slice of Kc, so for a certain range of Kc, you have also edge states which are helical, so spin up goes that way and spin down comes the other way. And so now the question is, if you are a purist, then you say this is not Majorana, but some people are happy. Say that's Majorana.
Okay, I'm sorry I had two questions myself, but I will have to move with the program on. Thank you, Manfred.